In the last section, we were talking about angle bisectors and perpendicular bisectors. So in this section, we're going to be talking about what happens when we have angle bisectors in a triangle and perpendicular bisectors in a triangle. So when we have three or more lines, rays, or segments which intersect at the same point, the lines are called concurrent lines or concurrent rays or segments, and the point where they all meet, that's called the point of concurrency. So we're going to be looking at what happens when you have three perpendicular bisectors of the sides of a triangle and the point of concurrency that they create. So when three perpendicular bisectors are drawn in the triangle, the point of concurrency of those perpendicular bisectors is called the circumcenter. And this theorem tells us about the relationship between the circumcenter, the point of concurrency, and the vertices of the triangle. So first you'll notice that each one of these lines, PD, PE, and PF, is a perpendicular bisector to the three sides of my triangle. In this theorem, point P, which is the circumcenter, is equidistant from the three vertices of the triangle, meaning it's the same distance away from A, B, and C. So these three lines here on the triangle, PA, PB, and PC, should all be the same length. So, why is P called the circumcenter? Well, it's really the center of a circle, and the vertices of the triangle A, B, and C are on that circle. So let's take a look at what we know about the circumcenter. The circumcenter P is equidistant from the three vertices. So P, right, the circumcenter, is the center of a circle that passes through all these vertices. So in the pictures below, the location of the circumcenter depends on the type of triangle, right? So you could have an acute triangle, a right triangle, or an obtuse triangle. In each one of these pictures, we've drawn the circumcenter. The circumcenter is the center of the circle. The circle goes around the triangle. And circum means to go around, right? So circumscribe. So think of some words that start with the prefix circum. Circumnavigate, right? That means to go all the way around or go around the globe. Circumvent, right? That means to sort of talk around a topic or to go around something. Or like circumference, right? To go around the circle. So the circle is going around the triangle, and P, the point of concurrency, is called the circumcenter. So the center of the circle that goes around. And of course, circumscribed means that you're drawing it around or writing the circle around. So notice in each one of the triangles, P is the circumcenter, and it's equidistant from all three vertices, because each one of those vertices is a point on the circle, right? And centers of a circle are equidistant from the points on the circle. So we're going to take a look at a construction where we can actually draw a circle around a triangle. So we're going to circumscribe a circle or draw the circle around the triangle. We should know from the theorem that we just looked at that the center of that circle will be the place where the perpendicular bisectors meet. So if we can just find the intersection point of two perpendicular bisectors, that will be the center of our circle. So we're going to start by drawing the bisector of side AB. So remember, to draw the bisector of AB, you're going to put your compass point on A, and you're going to arc out to the right and to the left. And now you're going to switch, move your compass over to point B, and arc again to the right and to the left. So you should have created two X's, one on each side of segment AB, and you're going to connect those two with a line. That's going to be your first perpendicular bisector. So we're going to repeat this process. We're going to find the perpendicular bisector of side BC, and then we'll look for where those two perpendicular bisectors intersect, and that should be the circumcenter. Okay, so remember, how do you find the perpendicular bisector of a segment? You're going to put your compass on B. You've got an arc on the right and on the left of the segment you're going to bisect. Move your compass point over to point C. Again, put your compass arcs, one on the right and one on the left, and you're looking for where those two arcs are going to intersect. We're going to connect those, and that's going to be our second perpendicular bisector. Do we need to make a third perpendicular bisector? No, because we know that it's going to just intersect right here at this point D. We already know where D is. So D is now the center of my circle. So you're going to place your compass point on point D and open up your compass so that the pencil is going to draw on one of the vertices. Now it doesn't matter which vertex you pick, A, B, or C, because remember, the distance from D should all be the same. So once you have your compass point on D and you've opened up your compass so that it goes out, let's say to vertex A, you're going to just twist your compass all the way around and make a circle around the circumcenter. Okay, so when you're finished with your construction, it should look like this. D is the place where the perpendicular bisectors meet, the circumcenter. And when we spin our compass around the circumcenter, we create a circle that contains all the vertices of the triangle. So let's look at some examples of some problems that we might solve involving triangles and circumcenters. So let's look at example 1. Example 1 asks us to solve for segment BG, given that G is the circumcenter. So we need to remind ourselves first, what is a circumcenter? And then secondly, what are its properties? Or when you have a circumcenter in a triangle, what do you know? So firstly, what I know about the circumcenter, G, is that it's equidistant from points A, B, and C. So notice that I've marked GA is congruent to GC is congruent to GB. That's one of the properties that we just talked about. If you have a circumcenter, it's equidistant from the vertices. So you'll also notice that GC, I'm already given that the length of GC is 9. And therefore, GB must be equal to 9. Okay, let's look at the second example. So in the second example, G again is the circumcenter. So remembering the properties of the circumcenter is that it's going to be equidistant from these three vertices, A, B, and C. So I'm going to mark that. Right? All those distances are the same. GA is congruent to GC is congruent to GB. So again, in my picture, they're giving me the length of GC. They're telling me that GC is 25. They're also telling me that BG is the expression 2x minus 15. So I should be able to set those two things equal to each other, right? So I'm making a substitution. GC is 25. GB is 2x minus 15. They have to be equal to each other because the circumcenter is always equidistant from the vertices. So now I just am left to solve this equation. I get 40 equals 2x. And I get x equals 20. So here are some examples of finding the coordinates of a circumcenter. So going back into coordinate plane geometry, right, and thinking about what are those formulas that we use when we work in the coordinate plane. We use the slope formula, the distance formula, and the midpoint formula. And sometimes we look at equations of lines. So let's take a look at this guy. It says, find the coordinates of the circumcenter of the triangle with the following vertices. So I'm going to start by plotting these vertices. So I've got A, B, and C. And then I'm going to connect those vertices together so I make a triangle. And I need to think about where does the circumcenter live, right? So to find the circumcenter, the first thing that I need to do is find the perpendicular bisector of side BC. So the perpendicular bisector, first of all, should bisect BC, which means that the perpendicular bisector should pass through the midpoint of BC. So again, using our midpoint formula for B and C, I'm going to take the average of the x's and the average of the y's, and that makes the midpoint at the point 3, -1. So right there. Because this is a perpendicular bisector, not only is it passing through this midpoint, the line, the perpendicular bisector line, should have the perpendicular slope to line BC. Now, because line BC is a horizontal line, all we have to do is draw a vertical line through the midpoint. Okay, so there's the perpendicular bisector of BC. Now, the circumcenter should be at the intersection of the perpendicular bisectors, which means now we have to find the perpendicular bisector of AB. So we're going to do the same thing we did to find the perpendicular bisector of BC. We're going to start by finding the midpoint between A and B. Using the midpoint formula, we're taking the average of the x's and the average of the y's, and we find that the midpoint of AB is right here at the point 0, 1. So that should be a 1. Okay, there we go. There's the midpoint. So perpendicular bisectors should be perpendicular to line AB, which means it should have the perpendicular slope to line AB. Now, since line AB is a vertical line, this line should be a horizontal line. So there's two perpendicular bisectors. Those two blue lines are my perpendicular bisectors, right? They're both perpendicular. They're both bisecting these two sides. And now I'm going to notice that these two perpendicular bisectors, wherever they intersect, that's the circumcenter. Right? So if these were two lines and I wanted to find the intersection of two lines, I could solve this as a system of equations. I could use substitution or I could use elimination. But in this case, because it's just two vertical and horizontal lines, it's actually pretty easy to find the intersection of these two lines, x equals 3 and y equals 1, actually. Let's fix that. And it's just going to be the point 3, 1. All right, let's try it one more time. Okay, so at this point you could pause the video and try this problem on your own, right? And then once you've figured this problem out, then you can take a look at the solution. So we're going to try this problem same way we did the last one. We're going to start by plotting the points, connecting our triangle, and looking for the circumcenter at the intersection of the perpendicular bisectors. So again, perpendicular bisectors, they always start off at the midpoint, right? And they always have a perpendicular slope. Okay, so there is one of my perpendicular bisectors. I'm going to do the same thing for line BC. I'm going to find the bisector, or find the midpoint of BC. I'm using the slope midpoint formula. And then I'm going to find a line which is perpendicular to BC, which of course is going to be a vertical line. and that is going to be the line x equals 2. The circumcenter is going to be right at the intersection of those two perpendicular bisectors. And it's going to be easy to see that the circumcenter should be at the point 2, 1. Okay, so that's what it looks like when you take the perpendicular bisector of each side of the triangle, right? We know that they're going to intersect at this point of concurrency, right, where they all intersect, and that point's called the circumcenter. But another way that we can look at a triangle is instead of applying the perpendicular bisector to the sides, we can apply the angle bisectors to the three angles in a triangle. Now this time the point of concurrency is going to be called the incenter. Okay? So the point is now going to be the center of a circle which is inside the triangle. So last time it was a circle that went around the triangle or was outside the triangle. This time the circle is going to be inside the triangle. Okay? And what we'll notice is that instead of having the vertices of the triangle be on the circle, now the sides of the triangle are on the circle. So here's our theorem about incenters. So the incenter of a triangle is equidistant from the sides of the triangle. So remember, the incenter is created by three angle bisectors intersecting. Okay. And we'll notice that PD, the distance from the incenter out to the edge, and PE, the distance from the incenter out to the edge, and PF, again, the distance from the incenter out to the edge, those are all the same. Now we have to be really careful here because it can be easy to confuse this picture with perpendicular bisectors because we see these 90-degree angles, but those 90-degree angles are there because we're measuring the distance out to the edge of the triangle, because we always measure distance with a perpendicular line. Okay, so be really careful when you see this picture. If it's perpendicular but it's not a perpendicular bisector, and we don't think that it looks like it's in the middle of the triangle, then it might be that we're actually looking at the incenter. Okay. So again, the incenter is created by three angle bisectors. And you can see that P is now the center of a circle which is inside the triangle, and points D, E, and F, which are points on the sides of the triangle, are on the circle. So now we want to take a look at how we would construct a circle within a triangle. Okay, now if I want to draw a circle inside this triangle, I'm going to need to find the center of that circle, and that's going to be my incenter. So the first thing I need to do is find the angle bisector. So I'm just going to pick one angle to start, angle A, and bisect angle A. Now remember how to bisect an angle. You're going to arc through the angle, right? So we're placing our compass point on the vertex, A, and we're gently arcing through the angle, right? Then we're going to leave these two intersection points. And from those two intersection points, leaving our compass on the same setting, we're going to arc out away from the vertex. So you see my two red marks, right? Those are my angle arcs. Now I'm going to connect where these two intersect back to the vertex. So angle bisector number 1 is finished, right? I've just bisected angle A. Those two angles are now congruent. And the incenter, remember, is where the angle bisectors intersect. So there's one angle bisector, and now all I need is one more angle bisector, and I will have found the incenter. So I'm going to bisect angle C. So remember how we bisect an angle. We put our compass on the vertex. We draw a gentle arc through the angle. We look for the 2 points of intersection with our arc and the rays of our angle. and then we draw arcs out away from the vertex. Once we find where those two arcs intersect, that point of intersection right there, we'll draw a line connecting back to our vertex. So there's our second angle bisector. Okay. And the point where these two angle bisectors meet, right, of course, is called the incenter. So D is my incenter. So I'm going to be making a circle. The center of the circle is going to be D. But instead of making the circle go around the triangle, the circle will be inside the triangle. So I'm going to open up my compass. I'm going to put my compass needle on D. And I'm going to open up my compass just so that it touches the edge of the triangle. And then I'm going to go all the way around and I'm going to draw my circle. So notice that the circle is just touching the edges of the triangle and completely inside the triangle. So that's what it looks like to inscribe a circle, or in other words, to draw the circle inside the triangle. And you'll notice that each one of these black lines from the center, incenter D, out to the edges, is the radius of that circle. Okay, so last examples here, and then we're all finished up. Let's take a look at some problems involving the incenter. So first of all, looking at problem 5, how do I know that problem 5 is an incenter? Well, you notice here that all of the angles are marked as being bisected. And as soon as I see all the angles marked as being bisected, that's how I know that P is the incenter. Okay? So if P is the incenter, then I'm going to apply some theorems that I know about the incenter, right? And that namely is that the incenter is the center of a circle inside the triangle. So if I draw this circle, this blue circle inside my triangle, that means that PS, PT, and PU are all radiuses of this blue circle. So if PU is 8, then it stands to reason that PT and PS would also be 8. And that's how we solve this problem. PS is equal to 8. Okay, we're going to do a very similar thing in example number 6. It doesn't say that the angles are bisected in the diagram, but it does tell us here to assume that P is the incenter. Okay, assume that P is the incenter. And again, we have to be really careful. Just because we see a 90-degree angle here does not mean we want to assume that PK is a perpendicular bisector. It very clearly is not bisecting QS because those two segments here and here are different lengths. So, knowing that P is the incenter, instead we know that P is the center of a circle, which is inside the triangle. If P is a circle in the inside of the triangle, then that makes PJ, PK, and PL all the radiuses of that blue circle. And that means that those segments are equal to each other. So now I can make a substitution with these values that they give me up here. I get 4x minus 8 must be equal to x plus 7. And then, of course, I can solve this equation for x. Am I finished? No. Because I wasn't solving for x, I was solving to find the value of pk. So I'm going to plug x back in to solve for pj. I find out that pj is equal to 52, and therefore pk is also equal to 52.